Now, here we have an assumption that a carbon bed is 2 feet deep, and of course the depth of the carbon will depend on the shape of the adsorption wave, which depends to a certain extent on the volatility of the solvent being adsorbed. Sometimes you can calculate a certain amount of carbon based on the working capacity, and you won't have enough area to meet a good superficial velocity. So that was the previous problem. We had to keep the superficial velocity at 70 because of pressure drop considerations. Well, this next problem deals with how to obtain an estimate of that pressure drop. So we're assuming the carbon is 2 feet deep. It needs to be to capture the adsorption wave, and consists of carbon that's sized between 4 and 10 mesh. We need to estimate the pressure drop. Okay, there are several ways to estimate pressure drop. And if you look in chapter 12, find a couple of equations and a couple of charts here. This figure 12.6 is the one to use here because we happen to have a 4 by 10 mesh carbon, so it exactly matches up with this line. If you're given some other parameters, let's say a 6 by 10 mesh or a 4 by 16 mesh, you can see it's not going to fall on one of these lines, but you can use these to estimate. The larger the number of mesh in the screen, the smaller the particles of carbon. So as they pack in more tightly, you'll get greater pressure drop. That's why you see these lines going up as the numbers increase. Here we have a 4 by 10 mesh carbon. We've got a superficial velocity in this question of 70 feet per minute, because that's what we had in the previous one. So we simply find the intersection of 70 and this curve, and there we have it, and that will give us the answer here. I read that as 4.5 inches of water per foot of bed depth, and that's the y-axis, pressure drop per foot of bed depth in inches of water. So where that intersection hits with 70 feet, it looks like about 4.5, and from that, simply multiply by the depth of the bed to get the total pressure drop. Okay, the next question, question 26, follows this tip number 11. We can never escape from having to know how to balance chemical reactions. And that's true in environmental engineering. It's probably true in every field of engineering, but certainly in environmental engineering, you must be able to stoichiometrically balance chemical reactions. And this is an example of where you would use that in a combustion type of reaction. So we have a tank of propane, say at a backyard gas grill, and we want to completely combust that tank of propane, and hopefully getting some good charcoal steaks during that process over a period of time. But nevertheless, we have 45 pounds of propane to burn, and that's about 400 standard cubic feet as a gas. Now, obviously, when it's compressed in the tank, it's a liquid, so it's not taking up near that much volume. A few gallons in the tank at most. But then if it were to be expanded to standard temperature and pressure and as a gas, it would take up about 400 standard cubic feet. So how do we go about solving this problem? Well, first and foremost, we've got to balance the chemical reaction. And there's the formula for propane, C3H8. We add the oxygen that's required, and it's going to give us 3 carbons, give us 3 carbon dioxides, 8 hydrogens, give us 4 H2Os, we add the oxygen back up, and we have 5 of them. So there's our balanced chemical reaction. Now, from here we can immediately see that 5 moles, 1 mole of propane requires 5 moles of oxygen. And since gases behave in the same proportions as volume as moles, we can simply conclude immediately that 1 standard cubic foot of propane needs 5 standard cubic feet of oxygen. Of course, we're not using pure oxygen, we're using air, and oxygen is 21% in air. So we simply take the ratio, 5 standard cubic feet of oxygen per 1 standard cubic foot of propane, divided by 0.21 standard cubic feet of oxygen per standard cubic foot of air, and we see that we need 23.8 standard cubic feet of air for every standard cubic foot of propane. Well, we have 400 standard cubic feet of propane, so simply multiplying that times that ratio gives us the total amount of air that we need. The only tricky part in this question might be that you're asked for the volume of air, but you need to balance starting with oxygen. So just remember this to make that conversion. Okay, the next problem deals with a pilot scale catalytic oxidizer. This might be a pilot system for an industrial oxidizer, it might be something for a car catalytic converter. But in any case, we've got a catalytic oxidizer providing a removal efficiency of 95%. The catalyst bed that was tested in this pilot scale was 2 inches in length. So we want to know the required length of catalyst in a full-scale system that is designed to remove 99.8%. Okay, here we have to go back into chapter 11 on combustion and look in the section on catalytic oxidation, and we come up with this equation. The concentration after passing through a length L of catalyst divided by the initial concentration is equal to the exponential of negative L over L sub m. And we can calculate L sub m for the system for this particular catalyst from the pilot scale data. Cl is 0.05 because we have 95% removal. So 0.05 over 1 is equal to e to the minus 2 inches over L sub m. Solving that for L sub m, we find that that is 0.6676 inches. Then we plug that back into the equation with a 99.8% efficiency for the full-scale unit, and solve that for the length of the full-scale unit. Turns out to be a little more than 4 inches. Now, in designing that, you may, of course, this is the answer that would satisfy on this particular question. You see your choices were 3, 4.2, 5.6, or 7.1. So you'd certainly answer that with B, the 4.2. But recognize in practice you may put in 5 or 6 inches of catalyst just to give yourself plenty of sort of backup or conservatism in your design. But in an answer like this, you want the required length or the minimum length of catalyst would be 4.2. So that's something to remember. Look at the question and decide whether they're asking you to design something and include safety factors, or whether they're asking you to calculate something and give them the answer that's being requested straight from the calculation. And it's usually this latter thing that they're asking for. Okay, question number 2.